So lovely.
No fan, turn it on.
Wait, click the. Turn the camera on so she can see.
No, oh, well, okay, there we go. Well, I don't blame
Do we
her.
have a camera on this?
No, we're blocking.
So you could, if you're on the bus or wherever you're going to be, you could eat with us as well.
Harrison and I plan to watch March Madness.
Okay.
How'd you say that?
I'm not trying to be calculus on a bus.
All right, so we're going to talk about parametric equations. And in pre-cal, we had parametric equations. My mic was not muted. Can you hear us, Sarah?
She says yes.
I muted myself,
Of course you did.
so you can't hear me cough.
Okay, well, fair enough. We just want to make sure you're still there.
Yeah, I'm here.
All right, so we're going to talk about parametric equations. And I emailed you all these documents.
Small.
Yes.
I'll take seriously.
He won't fall
Sure,
asleep that way.
absolutely, you may take Sarah's seat.
Thank you.
He just wants to.
Sarah, you've been demoted to the back of the room. Okay. Send an auditorium sitting to the back of the room.
Are we doing this freestyle?
Yes, freestyle notes, because you guys told me you didn't like PowerPoint.
What?
Who said that? Who said that? Who said definitely wait?
I'll stay away from her from writing and I'll have to take it notes.
That's dude.
Yes, it was not.
Yeah, bro.
That's Sarah. Sarah's here.
Sarah's here.
Okay.
Okay,
So much
There it is
sleep.
with us.
so let's remember, if you will, what a parametric equation is.
That's independent X and Y equations.
So it's going to be a set of equations, some function x of t and some function y of t that tells us where we are as a function of time. Or some parameter t squared minus 4, and this will be t over 2. And instead of being a point that's just an x and a y, we're going to have a point that's a x of t and a y of t. And it's really helpful in showing motion. So instead of drawing a function that just gives us an imprint on an xy coordinate plane, parametric equations allow us to realize that we might be at a certain location at a certain time, a certain point at a certain time. Okay, and we're going to primarily use this for position at time t. Okay, so I wanted to show you what a parametric curve looked like in Desmos, since we like to use Desmos, even though we can't use Desmos on the AP exam. But if you'd like to follow along on your calculator, you can do that. Let's do that. You go to mode, and we're going to change from function mode to parametric mode.
I always hated that.
Sorry.
I always hated changing the modes.
Yeah.
Well, I think it's a gift, a luxury that we can change
It is a
mode.
luxury.
So when you go to y equals, you notice that it is x of t and y of t.
Did you
Yeah.
have to use sequence mode to calculate on the last version?
No, you could have put it in.
Okay.
The good news is, no, you didn't. Is everybody on the y equals screen?
Yes.
Okay, so I'd love for you to type in our parametric equations, and now when you type, you're going to type t instead of x. Can you see t on your calculator? And I'm going to do parametrics on Desmos because it's easier for me to demonstrate. And on Desmos, to demonstrate parametric equations, you make it a point. And what is our function? It was t squared minus 4, is that right? So we go t to the second minus 4, comma, it was t over 2. And then you notice that when you type this on Desmos, you get the parameter limitations, right? So I'm going to just start at -2, and you should go to your window and notice when you go to your window that the first thing that pops up is T0. What is it? T-min. So let's start at -2, and then we'll make our T-max like 3. Okay? So let's see, -2 to 3. Now when you go to the graph, you go diamond graph, there's your curve. Now is that a function? No, it's not a function, but does it have slope? So this curve does have rates of change and it does have slopes. And we can have slopes of tangent lines to this curve. So there's some calculus that we can do with parametric equations. Interesting points here would be when the tangent line is vertical. When the tangent line is vertical, then we know we are furthest to the left or the right, depending upon what your curve looks like. So questions on how you do it on Desmos? Questions on how you do it on your calculator? Yes, no? Okay. Next thing is on your graph page, you'll see an F5. When you press F5, something will be highlighted, and it's called derivatives. Okay, if you scroll down and hit that arrow, you'll notice that the very first one is dy dx. Well, that's the slope of the tangent line. And then you're going to see two that are different. dy dt and dx dt. So dy dt is the rate of change of the y with respect to time, and dx dt is the rate of change of x with respect to time. So we have three different derivatives with parametrics, because x is changing with respect to time and y is changing with respect to time.
Is there anything related to rates?
Yeah, kind of, but just a little bit different. But let's learn the basics here first, and then we can talk about that, okay? So I'm going to take a picture of this. Maybe. Oops. Never works right when I'm live. All right. So what are interesting things we might want to know? We might want to know how to take the derivative so that we can find out the slope at a certain time. So the slope of the tangent line is always dy dx. But I have x of t and y of t. We have to figure out a way to deal with that. So I need to find dy dx, and I have x of t and y of t. Well, let me propose this. What do you think of this? Let's pretend our y is units and our time is in seconds. This would be units per second over units per second. And what happens to the seconds? They cancel out, and then we're left with unit over unit, which is dy dx.
So you just find the derivative of each.
Right, okay, so let's do that. All right, so finding dy dx here, we have to take the derivative of the first piece, which would be, now what's sometimes tricky is that people will get these split when they put it in the equation because y needs to go on top. So what's the derivative of y of t, dy dt? It's 1/2. Not all at once. And what's the derivative of the x, or x? It would be 2t. And we can simplify this. 1/4 or 1/. But wait, that means the derivative with respect to x, y, dy dx is a function of time. Does that make sense to you? Does the slope depend upon what time you are? It does, doesn't it? So let's say I wanted to find the slope of the tangent line somewhere, such that, let's say t equals, give me a number.
1.
1. So then we could say that dy dx here is 1/4. And I wanted to find the equation of the tangent line there. We need a slope, which we just found, and a point. So we have the slope is equal to 1/4, but now I need the point. So I need x of 1 and y of 1. So you have to go back to the top here and say, well, my function was t squared minus 4 in the x direction, so that's going to be 1 minus 4, which is -3. So my point will be -3, comma 1/2. And so we can come up with the tangent line here and say, all right, that'll be y minus 1/2 equals 1/4 times x plus 3. And then we can go back to our Desmos and see if we're right. So that would be y, we said minus 1/2, equals the slope we said was 1 divided by 4 times x plus 3. And we said the point of tangency was, I heard, was -3 1/2. So what do you think of that? So did we find the slope of the tangent line at a moment in time? So to find the derivative, you have to do dy dt over dx dt. It's really as simple as that. And then you have to find the point at a certain time. So the mechanics are not that difficult, really. All right, so let's say we wanted to find out where that tangent line was vertical, because that's an interesting place. How do we do that? Oop, I didn't mean to do that. I'm sorry, what? You said that very generally, but you were close.
And then we get the time, so we use the x to find the axis.
So when do vertical tangents occur, Keegan?
When it's that thing.
When the slope, yeah, how?
Is it a 0 in the
When you get a 0 in the denominator. So what is the denominator?
dx.
dx dt. So you get vertical tangents when dx dt equals 0. Think about that. That means when the rate of change of x is 0. Does that make sense, everybody? I mean, x is not changing, so its rate of change is 0. So we put this in the document. Make it smaller. So vertical tangents occur on parametric dx dt. Yeah, this is a very simple one. So this is 2t is dx dt. And this is going to equal 0 when t equals 0. But that's not going to give us the equation of the vertical tangent line. How do I figure out that? I plug this into, okay, so x of 0, what is that? -4. Oops. So let's see if that makes sense. I would love for you guys on your calculator now to hit that F5 button on the graph and the derivative, and you want when the x dt, press that button, and then you can say what, -4? And let's see what happens when you type that. What happens? Oh, we said t was 0, so plug in t equals 0, I'm sorry. What's it say? It says dx dt is equal to 0. That's what we expected, okay? So now what I want you to do is see the difference when you do dy dx. So do the F5, and then dy dx, which is the first one. And then you want at t equals 0, we want the slope. So what does it say to us? So what does that mean to you? Vertical tangent. Okay, so that's what you're going to see when you see a vertical tangent. Thank you. All right, and if you go to our graph up here above, you're going to see at -4, there is our vertical tangent. Where would we find horizontal tangents? When dy dt equals 0. On parametric curves, when dy dt is equal to 0, because that's the numerator. And in our situation here, dy dt was 1/2. Will this ever equal 0? It will never equal 0, therefore we don't have any horizontal tangents for this parametric curve. So far, the only difference with the calculus of parametrics is that to find the slope, you have to use dy dt over dx dt. Your points are defined with parametric curves as x of t, y of t. And your derivative, dy dx, is itself a function of time. So it's really pretty simple. All right. Well, guess what? We have to do some second derivative, don't we? I mean, because we'd like to know about concavity. I'm sorry? You want to know about concavity? I need to be honest. So concavity is still defined as the second derivative. So let's talk about that. But that's a function of x. Pardon me? No? I love how you're thinking that though. All right, so what is dy dx? Parametrically. I'm sorry? What's the...
The y is over next to
What is our derivative? Right? We have to, because the derivative is also a parametric curve. This is the most difficult part, the parametric piece of the derivative. So this is a function of time. So I could really write this as y prime of t, couldn't I? Theoretically, I mean, could I write y prime of t and that equals 1 over 4t? So then I could say that 1 over 4t goes here in the y spot. Well, I should say yt. What about x? Where I'm standing is still a function of time in the x position. So this is just straight up x of t. That's the hardest part to get. And what did we say x of t was?
T squared minus 4. Oh, that's the y. That's the y.
Oh, I'm sorry, t squared minus 4. You're right. Because the slope is to find where I'm standing at time t, which is what this is. Not the rate of change of where I'm standing. Does that make sense a little bit? So if I was going to find the derivative of this, what do I have to do? So you're going to do the derivative of, with respect to time of y prime of t, which is dx dt, I mean dy dt, sorry, over dx dt. So let's do that here. What happens? One-fourth, or negative 1/4, 1 over. I can't remember, be able to write it better than I can say it. Do you read that? Over. Two t, yes. So if I were to simplify this, is really 2t over 1. So that would be negative 1 over 18 cubed. So then your concavity function, your second derivative, is going to be also a function of where you're standing at time t. All right, so let's use the point you guys gave me a moment ago, which was at t equals 1, right? Sam? Let's try at t equals 1. What would our concavity, or our second derivative be? Negative 1/8. So what does that mean when we are at t equals 1? The time equals 1? You're concave down. Now what was the point at t equals 1? Was it 3, negative 1?
Negative 3, 1.
Negative 3, 1/2. Now let's go back, refresh our memory banks. We have 3, 1/2. Are we concave down? You see how it works? So the trickiest part of the second derivative is that you have to take the derivative of y dy dx, which is a function of t, over dx dt. That's the trickiest part. calculus and parametrics. But wouldn't it be nice to know how long that curve is?
It would.
Oh,
Minus.
Square root. It'd be nice to know how long that curve was.
Be nice, but we don't really.
What do we call that?
I mean, it'd also be nice.
Oh, Mr. Dudar, what do we call that when we're finding the length of the curve? Begins with an A. It is arc length. And he's getting that comfortable position again.
That is a comfort position.
So, arc length, we need to talk about that really quickly because parametrically defined curves have arc length. All right. So, can we recall what the arc length formula was? Well, we had to have that first. From A to B of square root.
1 minus ui dx squared.
Do you remember that?
But if you take that, make it more complicated, that very much here, because of UID, so UID.
What? Oh, yes, okay, I love it. You're already going there. That's great. But what is this going to be? Instead of A and B, this will be times 1 to times 2. So it'll be the integral from time 1 to time 2 of the square root of, and Mr. Dudar, you were right, this will be 1 plus now
UIDT over the SDT squared. Yes.
Was it not DT?
It would have to be dt, yeah. Now let's think about, that looks pretty messy, doesn't it? You got a double decker fraction. May I find a common denominator here? Yes or no? Actually, yeah. So this is still T1 to T2. Square root of, what would the common denominator be? The x dt squared? So this would be the x dt squared plus dy dt squared over the x dt squared. Now, obviously, the square root thing goes all the way down. So that's going to cover that. Actually, you know what, guys? This is dx until we can cancel it out. This is dx until we cancel it out. So just bear with me. So what happens? Can we take the square root of the denominator? We can. And then this would be dt over dx times the square root of dx dt squared plus dy dt squared dx. And what happens? The dx's cancel. And then we get the arc length for a parametric curve. That wasn't too difficult, was it?
It wasn't really fun though either.
So we're gonna try to find the arc length of the curve that we have. Okay. What was our curve? We said it was x of t, which was equal to t squared minus 4. I'll try to remember that accurately. And y of t, which was t over 2. So then we could say that dx dt, as we were so correct saying earlier, is 2t, dy dt is 1/2. And we have this curve defined, didn't we say, didn't I say from -2 to 3, isn't that what I said? And so we can find the arc length of this curve. Let's see what happens here. That's going to be the integral from -2 to 3 of the square root of, well, what is dx dt? So that would be 4t squared plus 1/4 dt. Sadly, we can't integrate that unless we use trig substitution, which I'm not ready to go to today. So somebody has to do this on the calculator for me. You're not going to have to do it on the AP exam or for me, okay? That's just another methodology that's not in the BC curriculum. I wish it was, but nor do we have time for it.
I thought keeps asking me if we've done it yet.
No, we're not, yeah, you're not going to do it in high school. Okay, sorry, unless we have some time after the AP exam, which I know you guys are so thrilled to do. Right?
Absolutely.
Or no, I think y'all will be done. Okay, so somebody give me an answer. I need 3 digits, so
0.435
units. So that is the length of the curve.
Which one area under the curve?
In parametrics?
Yeah.
No.
Do we have to, it does position, do we ever have to do velocity acceleration?
We're gonna do that with vectors next time.
Is it different from parametrics?
Technically, no.
We say next time.
I mean Friday, yes. Okay. Anyway, so questions on parametrics. What I have handed out to you is a parametric AP style when time really matters. You know, my silly hokey, little things I like to do. So I was thinking about doing the 2016. Would you like to do the 2016? Which number one?
So I do like XKCD.
I do. Although sometimes even XKCD is above my head. So let me open mine.
It's over my head half the time, but I'd like to think I can appreciate it.
Yeah. The XKCD guy is a physics person.
Let's go on it.
Please.
But apparently, biologists and great because going to one day because the world is their time. You cuttlefish. I remember, I will take over the world with cuttlefish. That's exactly the kind of world domination plan I would use. You can help me.
All right, so here we go. Hopefully we'll finish this in the next 10 minutes. We finish this in the next 10 minutes, we'll have some free time in DC conference, which is a rare. What? Here we go. So, number one. This is question number 2 on the 2016 exam, which means it's calculator active. All right? So, This question states, at time t, the position of the particle moving in the xy plane is given by the parametric function x of t, y of t, where dx dt is equal to t squared plus sine of 3t squared. The graph of y, consisting of 3 line segments, is shown in the figure. So they're giving you dx dt, and they're giving you dy dt graphically. All right, it says at t equals 0, the position is 5, 1. So right away, when they give me an initial condition like that, I am going to set up a function for x of t before we even start. What's x of t going to equal? It'll equal the integral from 5, or wait, from time equals 0, right, to some time, and then I'm going to put my derivative here, which would be x squared, I'm using a dummy variable, plus sine of x squared, or 3x squared, sorry, dx, plus, if what happens when time is 0, I get 0, so I need to get 5, so I'm going to put plus 5. So I've got my position function. What would my x function, what would my y function be? The integral? 0 to t, and I'm going to put dy dt here because I don't know whatever this is, right? Or should we say, let's put y prime of x. Would that be better? Dx plus 1, good. Find the position at time equals 3. What do they want you to do? So we're going to use these integrals, and this you cannot integrate by hand. So you're going to type that integral in your calculator. So for part A, we're going to do x of 3 equals the integral from 0 to 3 of x squared plus sine of 3x squared dx. You don't have to. You're just going to do it on the home screen, aren't you? I mean, you just have to be in grads. The calculus is grad. Would somebody give me what the x component would be? Thank you. 14.377. Okay. Do I get concurrence? Now you can truncate it or you can round it up appropriately. What do I mean by truncate, Mr. Dudar? Cut it off. So you can go 3 decimal places and then just cut it off. The AP people will accept either the truncated or it rounded with the next digit. But you have to have 3 DPs. All right, now what about y of 3? That's the integral from 0 to 3, God bless you, of y prime of x dx plus 1. All right, well, what is the integral from 0 to 3? It's the area under that curve. So what are we going to do? Well, we have a trapezoid and a triangle. How do I figure out what that intersection point is? The 0. Do these cancel? We don't have to worry about that, right? The other one will also cancel.
The other end adds on, so it's 2.
Yeah?
I have a question.
Yes, sir.
Why are we talking about the derivative of the, or like, why are we talking about like integrals when this is just like the y position function?
It's asking you for where it's standing at time equals 3. And they're telling us that this is, they tell us the x dt, which is the rate of change of x, and they tell us the y dt. And in order for us to find out where we're standing, we have to have the x and the y, not the rates.
Okay, I guess I'm just asking, why couldn't you just take the slope of the line from 2 to 4, take that slope over your dx over dt, and then plug in t equals 3. You see what I'm saying?
No, I don't.
Because this is just like the y position function of this graph. And then why couldn't you just take that? I don't know.
Why can you just?
Because it's two-dimensional position.
Yeah, with the dy over dt. So you take the slope of the last like segment on that graph. Take that
Okay,
slope.
can we do it my way and see if it matches yours?
Yeah.
Is it matching it on the x already?
Yeah, but okay. Yeah.
Is it?
It was. We did the same way in the first one.
Okay. All right. What's the area? That's left. It's negative, right? I'm looking for this area. Because these cancel each other out? Yes.
Oh, we're just doing 0.
You go to 0 to 3 though?
Oh, 0 to 3, yeah, sorry.
So it'd just be the area of 3 to 4.
But it's subtract 3 to 4, yeah.
I need the area from 0 to 3, don't I? Yes or no? It's a square, which is 1. For the category? You guys have the right goals in mind.
7 4.
That was going to be good, 7/4? Thank you. So this is going to be 7/4 plus 1. That's negative 7/4. Negative 3/4? Why is it negative? Mhm. Did you get that same position?
I'm just like, isn't the graph at the top? Isn't that just y of t and not the derivative of y of t?
Oh, it is, it is.
Yeah. That's what
I'm
I was just
sorry.
confused about.
I'm so sorry.
That's what I'm saying. So we don't have to integrate.
Yes, I was under the misassumption that that was the derivative, right? Because they gave us the FTD, what did I do? Jake, you just gotta stand up and say, Mrs. Muller, see, that's y of t. I didn't understand what you were saying.
Well, I looked at, I'm like, what the heck?
I'm human, yes? Everybody see that? I thought that was the derivative of y. And you all were so polite except for Jake. I'm sorry. I'm not saying he's ill-mannered, he just needed to be less polite and let me know what the reality is. All right, so that's y of t, yes? I feel like an idiot, Sarah. Can you speak to us?
There's no way she's doing it.
Yeah, she's totally failed.
She's getting fit or something.
Yes, probably is. All right. I'm sorry. So what do we need to know? That's the curve. We need it at 3, don't we? And that's negative 1/2.
And then these are easier, right?
I hope.
It's just dy dx.
So y of 3 is negative 1/2 from the graph, okay? Find the slope of the tangent line to the path at t equals 3. So we need dy dx, which is dy dt over dx dt. I was making it harder than it had to be. Now, the AP people are going to want to see this comment right here. God bless you. This is the calculus, isn't it?
Then you have the x dt and dy dt.
So dy dt is the slope. Jake, what is the slope for us there? At 3.
1/2.
1/2. And then the x dt, which we stick in our function at 3, our function here, you guys put that in your calculator, you're going to get a number, right? That's not very nice. So I'm going to put it at 9 plus the sine of 27. Yes? Is it 3t squared? Now, before we go any further, I'm going to tell you that this would get full credit right here. Leave it like that.
Did you get any new information from?
I did, but it's on series, so I'm going to save that. Is that all right? Because I attended a session called "Are You Serious?"
Oh my goodness.
Serious. And I thought to myself, I thought to myself, gosh, I'm right at home. They are being
The math puns at Universal.
honey just like me. All right. Does that give us a number to 3 decimals? You want to give that to me? Anybody?
I was wondering, how long is like a conference on series?
It was about an hour. That presentation was an hour. I'm sorry, decimal here?
About 0.05.
0.0. Thank you. Part C, find the speed.
No, it's 0.0.
Oh, yeah.
It's like 0.0.
Yes, but I'm only showing
These truncated.
3. I truncated it. And rounded, because it's the same, right? Yeah. The speed of the particle.
It's the same thing as
Speed
absolute value
of the magnitude of the velocity, isn't it?
Isn't it 0.05 magnitude of velocity?
We haven't talked about what the velocity is.
That's like subquadratic.
It is, but we're going to talk about it real quickly right now. Do we remember what vectors are?
Something with I and J.
Physics.
Oh, goodness gracious. Just really quickly, remember we used the angular, yeah, there it is.
Muted.
Okay? That's position. This is the position vector. And what does a position vector do? It points to your position at time t. That means its tip is where your position is. So if this is a position vector, that is where your position is. The arrow is pointing to where you are. And if I were going to do a vector-defined function here, your position function is moving at different times, so it's like you're riding on the top of the position arrow there. And that's what's creating your vector-defined function. Okay? Those have velocity, don't they? Or they have tangent lines or rates of change? I'm going to physics.
That's where you're going.
Right? That's where you're. They're tangent. The velocity vector is tangent to this one. And it points in the direction of motion. Okay, so the velocity vector is going to be x prime of t, comma, y prime of t. And there's obviously an acceleration vector. Oh, I meant to, I'm sorry, yeah. Now, that's the velocity vector. This is giving you the direction of your velocity. But a vector has magnitude and direction, okay? So the magnitude of the velocity vector, and I'm gonna, remember those bars? That's the magnitude. Is equal to yeah, and another way to write it is dx, whoops, dx dt squared plus dy dt quantity squared. And this is a scalar.
So what's the point of finding tangent lines to a parametric if it's not the velocity?
Because the biggest application to parametrics is physics.
But you get nothing from the tangent line. What is, in physics, what would the tangent line of a parametric represent?
Unit per unit. Not very helpful, is it? I don't know what else to tell you.
That's fine.
So they want to know what the magnitude or the speed is. This is also known as speed here. And speed is a scalar. Oh, come on. Speed is a scalar. It's got no direction. You guys, how old are we?
Very, very.
So what are they laughing about? Younger kids will laugh at speed.
I know.
I like the speed this one.
I'm so happy. All right, so what are we going to do? We want the speed at t equals 3. I got 3 minutes. Let's do it. So this was that we want the velocity at 3 magnitude. So we need dx dt. So you have a calculator, don't you? So that's going to be at 3. It's going to be 9 plus sine of 27. Is that right? Squared plus. What is the slope at 3? You guys told me. 1/2 squared. I don't, oh, let's see, no, don't know it. No, not commentary. Okay, calculator people. Technology people, with your phone, you'd be out in a dark calculator.
I'm not sure about that.
Calculators
suck. They do.
Let's do
Oh, I didn't get it. I got a 9. Wait a second, I got 9.
Is that right? I'm sorry, what?
That's not right. 9.9. I'm in radians.
9 point, help me,
9.969.
units per time. Did they give us any time? They didn't. Total distance traveled. Okay, total distance traveled in Vectorville. Time 1 to time 2 of the magnitude of the velocity, which is What do you say, Miss Olivia? What does that look like? Magnitude velocity, what does it look like?
Are we still in first?
No, this is D. So this problem foreshadowed to use vectors and parametrics. Or parametrics, or vectors and vectors, right? Okay, so we needed total distance travel from 0 to 2. Oh, I heard you yawn.
Look up, Sarah.
It's probably gone now. So what do we do here? Square root, I mean the integral from 0 to 2, square root of, what is the dt? We know it is as t squared plus sine of 3t squared plus So we have to do two integrals, don't we? We have to do it from 0 to 1 plus 1 to 2. Why? Jake?
Good afternoon.
Yes,
A
so
few afternoon announcements before our closing prayer. So students, please pay attention to those. First, today's boys JV tennis match has been canceled. Also, all boys varsity and JV soccer practices are canceled for today.
For the first, was it 1?
So if you're part of the boys JV tennis or boys varsity or JV soccer teams, then listen to this next one. The track meet this afternoon is a marquee event, so go out and support our track team. If you attend this event, you will need to sign up at the concession stand for house points.
And bring your very warm jacket.
Our track teams today. A couple of students need to go places. Aiden Foley needs to see Mr. McCarthy, campus ministry. Kristen Glowacki and Kyle Swade need to see Mr. Stevens after school. And then one quick announcement about course registration. There was a little bit of confusion regarding AP Physics 1 and contracts and all of that. If you are signing up for AP Physics 1 for next year, you do need to get a contract. You can get one from your current science teacher. You do not need approval to take the course, but you do need to turn in an AP contract for AP Physics 1, so just be aware of that. Please stand for afternoon prayer. In the name of the Father,